determinants of matrices. So we're going to learn some new definitions. We've learned the identity matrix already. Identity matrix is always in a square matrix where the main diagonal is all ones and everything else is zeros. And we're going to find out that the determinant of an identity matrix is always 1. So what is a determinant? Well, it's a number. And it's a number that you can find by multiplying this diagonal. And actually, this is the way that I find it the easiest way to memorize, because you don't have this formula on your formula sheet. You'll have to know how to find the determinant. And it's easy to memorize with the following arrows. This, multiply those, and that value is going to be whatever it is. And then you subtract that arrow. So you multiply along your diagonals, and you take A times D, and you subtract B times C. And there's two ways that you can see or that you can write determinants. You can either use DET in front of them, that's sort of what your calculator does, or you can use sort of absolute value bars around a matrix, is asking you to find a determinant. So if I'm asked to find a determinant, I think of this one, I get 8. I think of this one, I get -9. And then I would take 8, and I would minus the -9, would give me a determinant of 17. Second one, 36, 36. 36 minus 36 would give me a determinant of 0. Now, determinants only exist in square matrices, and we call matrices that have a determinant of 0 a singular matrix. And a singular matrix does not have an inverse. So we're going to learn about inverses of matrices. This one would have an inverse. This one here would not. And we're going to find out. Again, we're right now just setting things up so we'll be able to do some solving with matrices. Okay. How do you like that formula for the determinant of a 3 by 3 matrix? Basically, what you're going to do in this formula is you start with A, cancel out everything in the rows and columns, and multiply it by the determinant of what is left. Okay? Then you go to B, cancel out everything in those rows and columns, and multiply by its determinant. Then you go to C, and same idea. Take C, cancel out everything in those rows and columns, and multiply by the determinant that is left. That's the memorization way to remember that formula. And then it goes positive, negative, positive. But I find that the straight, you can do a similar thing that we did in the 2 by 2, because I find those arrows really easy to remember. We can do a similar thing with a 3 by 3. You rewrite the first 2 columns, and that will give you 3 diagonals in the positive direction. So you would put all of these ones and add them together in the positive direction. And then you would have 3 arrows in the negative direction. You would add those together and put a negative in front, and then you take the blue ones and subtract the red ones. Which is a lot easier as a formula to remember, because then you just have, oh, I just have diagonal lines. I don't have to remember plus or minus or certain determinants as I'm going. So this is what it's going to look like if we solve one like this. I'm going to take the first two columns and rewrite them. 2, 1, 2, negative 1, 2, 1. I've got this diagonal, 2 times 2 times 2 is 8. This diagonal, 0. And this diagonal, 4. That will give me 12. And then I'm going to subtract this diagonal 16 plus 0 plus negative 2. And I get a determinant of negative 2. Now, if we take out our graphing calculators, and we enter this matrix in, so this is a 3 by 3. Negative 1, 4, 1, 2, 0, 2, 1, 2. So now I put this in as matrix A. If we go to matrix and go over to math, there's a bunch of things that we can do with our matrices. The very first one says determinant, so I can say I would like to find the determinant of matrix A. So I type that into my calculator, and it tells me negative 2 as well. Whew. So I find that this diagonals method works really nice. Try this one on your own. All right, check. Did you get 30? So we do the diagonals in one direction. Diagonals in the other direction, and you get 30. So now we can, again, you can use this, and the next little bit here, I go into, hey, we can, calculator can do a bunch of these things. It has the determinant. It has a little, the T, you can do the transpose. One of the ones that's going to be really interesting to do is this RREF, which stands for Reduced Row Echelon Form, which is pretty cool because check this out. We're going to go back. So this last one that we just did, 303, negative 2, 1, 5, 4, negative 2, 0, that 3 by 3 matrix could be the coefficients of some system of equations. Notice how we started this unit with systems of equations. And it could be equal to 3 different numbers. So I'm going to go to my calculator, and I'm going to put the blue numbers in and the green numbers into a matrix. So second matrix, edit A. This time it's going to have 3 rows and 4 columns. And I'm going to put the 3, 0, 3, 5, negative 2, 1, 5, 2, 4, negative 2, 0, 7. I should really make you solve this one with substitution and elimination by hand first. Because just to, do we remember how we solved these ones? We practiced them. We would pick something to cancel out first. I would probably cancel out the y's. Because you see a y is already gone in equation 1. And then I would take equation 2 and multiply it by 2, then add it to equation 3. That would easily get rid of another y. And then you would have 2 equations, this one with a, whatever I get left with b, and then I would be able to solve for either x or z next and solve it completely. Watch the following. Okay, so we've got our new matrix in here, and we're going to go to matrix and go to math, and go all the way down. There's ref, and then there's ref. So both the ref and the ref are very helpful. We'll do the ref first. We're going to put that, enter that for matrix A. And it does the following. Then even I can do this. Math, fraction. There we go. It did the following. It changed this to this. So I'm going to rewrite this out as, right, the same coloring. 1, oh, it's not the same. Failed already. 1, 0, 0, 0, 1, 0. Look, oh, what did it make here? It made an identity matrix there. And then my green numbers weren't pretty. Oh my goodness. 1730 negative. Can't even remember them all at once. And 11 or 10. Hey. X plus y plus y plus z. It took the same matrix we had and reduced it and changed it to this. What's really nice about this new equation is how hard is it to figure out what x is? Look at equation f. It's like, ooh, 1x plus 0y's plus 0z is 17 on 30. So what's x? Oh, I know what x is. I love solving these equations. What's y? Oh, it's already there for you. So it took this equation. Now check it out. If we just check one of these equations, according to this, I'm going to take out my calculator again. I'm going to clear this out. According to this, if I take 3 times 17 divided by 30 plus 3 times z, 3 times 11 divided by 10, oh, it's 5. Isn't that nice? We could, oh, what about the second one? We could, and I can tell you right now, we could try all 3 of those with those numbers, and they would work. So we just, by putting buttons into our calculators, instantaneously got all the solutions for that 3x3 systems of equations. Our job now is to figure out why does this work, but this button on our calculator with the reduced row echelon form is going to be very handy to check answers. The reason we learn determinants is determinants help us with inverses. And one of the things in our properties was that if you have an inverse and you multiply a matrix by its inverse, you will always get the identity matrix. Again, the identity matrix is the one with 1s along the diagonal and 0s everywhere else. How do you find the identity matrix? Well, here's the formula for a 2x2. You find the inverse of a 2x2 matrix by calculating the determinant, and you put the determinant as a fraction on the bottom. And this is one of the reasons when before I said if the determinant of a matrix is 0, the inverse doesn't exist. And the reason is because in this formula, you have to do 1 divided by the determinant, And if the determinant is 0, you're not allowed to do that. So we do 1 divided by the determinant, and then we do this crazy formula where you take the diagonal numbers, you switch them, and you take the other diagonal and just make them negative. So if you have any 2 by 2 matrix, this becomes the inverse. All right, so we're going to do some questions with these. Find the following inverses. So first of all, we could figure out the determinant, and if I was showing my work, I could use straight lines here to do the determinant. The determinant is going to be this diagonal, 6, minus this diagonal, 5, is equal to 1. So then my inverse, and I'm going to let this equal A, so I can write A inverse is going to be 1 over my determinant 1. Switch this diagonal, 3 and 2, and make the other diagonal negative. So I get 3, negative 1, 5, and 2. We can check what is A inverse times A. Well, here's A inverse. And here was A. And you see that you're allowed to multiply these because this is a 2 by 2 times a 2 by 2, and our middle numbers match. We are going to get as an answer a 2 by 2. How do we multiply matrix? Well, I'm going to find row 1, column 1 first. So I'm going to do that one in green. Row 1, column 1. Take that row, turn it, crash it in. You see that you're going to get 6 and minus 5. Add them together. You'll get 1. Next, I'll use purple. I want to find this one. That is row 1, column 2. Turn row 1, crash it in. I'm going to get 3 and negative 3. You see that you would get 0. Next color, this one, orange. That's row 2, column 1. Turn it, crash it in. You're going to get negative 10 and 10. This one's going to be 0. And finally, bright yellow. This one right here. Row 2, column 2. Crash them in, negative 5 and 6. You can get 1. And we get the identity matrix. And if you have an inverse multiplied by its irregular equation or regular matrix, you will always get the identity matrix. So we can find an inverse by calculating the determinant. After you've calculated the determinant, you switch the main diagonal and multiply the other diagonal by a negative. So try the second one on your own. I'll put the answer up in a bit. All right, let's see. I'm going to call this one B. B inverse. Did you correctly figure out that the determinant was 3? So you'll have 1/3. Switch the main diagonal. Multiply the other diagonal by a negative. And there's your inverse. Okay. So, what we said before, because we need to divide by the determinant, right? If the determinant is 0, as in a singular matrix, then you have no inverse. We can check by typing things into our calculator and just using the X inverse button. Right? So I had a big matrix A in my calculator that was a 3 by 3. I could go second matrix. Here. This one's a 2 by 2. So you can only do inverses of square matrices. So I take my 2 by 2, and then I just hit the -1 button, and it will find the inverse. Wow. You can change things to fractions to make them look nicer. What was matrix B? Just curious. Second matrix B. I don't remember what I had. Oh, it was a nice big one. That was from our sick grade 11s and 12s. Right? Apparently that's the inverse, but check this out. If I take this one right here, this matrix, oh, it didn't let me select it. Didn't like that? No, it didn't. Okay. I am going to take second matrix B. Oh, took B, did the inverse, and then I'm going to times it by second matrix B. So here's the inverse of this one, times by B, and what do I get? I get 1, 0, 0, 1, the identity matrix. All right. So where is this going to help us? Oh, we're first going to do 3 by 3 matrices. For 3 by 3 matrices, you have the option of either using a graphing calculator and getting the inverse within seconds, or looking online at the one-page formula for 3 by 3 matrices, memorizing that and using it. It's totally up to you. Oh, everybody took out their calculators. So what we're going to do is we're going to go to our calculator. We are going to go second matrix and edit this. We're going to put in a 3 by 3. 1, 1, 2, 3, 4, 1, 1, 3, -2. And once we've got our 3 by 3 matrix in there, we can quit. We can go second matrix A and hit the inverse button and push enter. And again, it will come up as decimals, but if you hit the math button and number 1, change it to fractions, it'll be much easier to write your final answer. -11.6, 4/3, -7.6, 7/6, -2/3, 5/6, 5/6, -1/3, and 1/6. So now, just for fun, we are going to say, hey, I already know how to solve this equation in a much easier way, but now I would like to use what I just learned and do it in a different way, okay? So I totally understand where you're not going to appreciate matrices yet. Because right now, I hope that if I was doing this one, I would be like, ooh, I'm going to subtract because that eliminates my x's. -2y subtract a y, that'll give me -y. -2 subtract -11 will be -2 plus 11, which will be 9. And so y is equal to -9. That was so hard to figure out. And once I got y as -9, I could use either equation. I'm going to use the second one. 4x minus a -9 equals -11. 4x, move the 9 over, equals -20. And x is equal to -5. So my solution to this system of equations these two lines are going to intersect at -5, -9. But I'm so excited about the fact that I just learned about matrices and inverses of matrices that I'm going to develop a new technique to do this same question that you already are comfortable doing with an old technique. Right? But sometimes when we figure out things like this, okay, we're going to solve this, and I absolutely want you to still like this method the best, because it is a better method than what we're about to do. However, when we get to bigger ones, then all of a sudden you're like, ooh, with my calculator, I appreciate matrices, because I can solve a bigger one easier than this technique. So there's a give and take. So for the 2x2, this technique is not going to be as good. But what we're going to do is we're going to take this equation. We are going to make a matrix with the coefficients. 4, -2, 4, and -1. We are going to make a matrix with the variables. We're going to put an equal sign and make a matrix with the answers. Just to check, okay, I want you to be aware that by doing this, this is a 2x2 and this is a 2x1. Can you see that they could multiply together? How do you multiply matrices? If I multiply them together, I'm going to get a 2x1. If I want to figure out this one in blue, this is row 1 times column 1. I would have the 4 times the x, and then the -2 times the y, and add them together, and I would get 4x minus 2y. It's still equal to this matrix here, which had -2 and -11. Like that. Can you see that this is just this equation put into a matrix? That the top one's equal to the top one, and if I multiply the bottom one out, I would get 4x, right? This one, and this one, minus y. We have the same equation, just written as a coefficients matrix and a variables matrix and an answer matrix. Next, we think of the coefficients matrix as A, the variables matrix as X, the answers matrix as B. If we multiply and wanted to solve for X, there is no dividing in matrices, but there is an inverse. If you multiply A by its inverse, you are going to get the identity matrix, and the identity matrix times anything keeps that thing the same. So in a sense, this will get rid of this and just leave us with X. Okay? Here's the tricky part that's different than regular equations. Because matrices is so important, the order of multiplication, if you put the A inverse in front there, you have to put it in front there. It will not work if you put it in front on one side, but behind on the other side. And so the equation that we already solved algebraically quite easily with elimination, we are now going to do with matrices and inverses, and it will be a little bit not as easy. Okay, but this is what it would look like. Okay, here's our matrix A, 4, -2, 4, -1. Here's our variables matrix, X and Y. And here's our answers matrix, -2 and -11. Okay. We are going to, and I'll write it in green in front here, we are going to find the inverse of 4, -2, 4, -1. And put it in front on both sides. How do we find the inverse? Well, we need the determinant. Can you see the determinant is going to be -4 minus a -8? The determinant is going to be 4. So in our inverse, we'll have a 1/4 out in front. And then we switch this diagonal and make this diagonal negative. So we'll have to write that here as well. -1, 4, 2, and -4. This whole part, an inverse times itself, will be the identity matrix. That will simplify to just be 1, and 1 times anything is just 1. So we will be left with, on this side, just x and y. And on this side, we're going to have to multiply. Now, my recommendation is to keep the 1/4 out in front to start with, and take this 2 by 2 and multiply it by this 2 by 1. Notice your middle numbers are the same, and your answer here will be a 2 by 1. To find the top number, you would take row 1 and multiply it by column 1. Can you see that you would get 2 plus -22? You would get -20. And I'll color code this one in orange. If I take row 2 times column 2, I'm going to get 8 minus 44, which is -36. So I would do the 1/4 last just so you're not dealing with fractions. Now you can multiply that 1/4 in, and you would get -5 there and -9 there. Are those the same answers we found algebraically? Do you like the elimination better still? Yes, that's perfectly, that's good. It's right. Sometimes we just have to appreciate that this is wonderful, that you've developed this math that figures this out, but I don't know how helpful this is because my old technique is still more efficient and faster. Right? I'm still waiting for the year that a student puts their hand up and says, I found the fastest way yet, Mr. JR. Get them right every single time. I just look at the answer at the back of the book. And I write that down. I haven't got one wrong yet. Unfortunately, my technique hasn't worked very well in quizzes and tests yet. But if you provide the answers, I'm sure it will. But if we're allowed a calculator, right, this could be really nice. Again, so we're going to practice, and we're going to do this without a calculator. I'm going to let you try this one on your own. In fact, I'm going to let you try the next 2 on your own. I forgot I was going to give you time to work on word problems. I guess I have to do that tomorrow. Here's the setup and the check for the first one. So sometimes what I do after I set it up, I kind of go, okay, this is matrix A, this is matrix X, this is matrix B. I'm going to need to multiply by my A inverse in front. That for sure will just get x by itself. So sometimes writing it this way saves me writing, because then I can just write matrix x is equal to 1/5. There's our inverse matrix right here. Multiply by 5, 0. Again, I would multiply out the whole numbers first and leave the fraction to the end. And when you divide everything by 5, you get 1 and -1. For the second one, you first would have to do a little bit of multiplication, multiply everything by 4 to get rid of that fraction, rearrange things so that everything matches up so you can make your matrices. And you can keep working on it, but I'll put up the answer here so you can see how you did.